Integration by parts. So when looking for antiderivatives, occasionally we start with a function that came out because of the product rule. So remember, when we do the product rule, we're taking the derivative of one function times another function. So let's start by looking at the product rule and see how we can do some manipulation to undo the product rule and get our formula that we're going to use for integration by parts. When we do the product rule, we have one function times another. Now, we usually use f of x and g of x, but the formula here is going to use u and v, but it works the same way. So remember, u is a function of x and v is a function of x. We're going to remember that so we don't have to write the of x the whole time through. So if you take the derivative of u times v, you have the derivative of u times v plus u times the derivative of v. This is the part of the formula we're going to be working with. So this is the product rule. Notice the term in red is u times v prime. If we solve for that, we can subtract the blue term over, and we get uv prime equals the derivative of u times v minus u prime times v. Now, these are still equal because all the things we've done so far have been mathematically legitimate. Now we want to find the antiderivative of every piece. Since these things were equal to start with, then the antiderivatives also will have to be equal. So the antiderivative on the left becomes the antiderivative of u times v prime dx. Remember, u and v are both functions of x, so we have dx. And then we take the antiderivative of each term on the right. Now, since the right-hand side was separated by subtraction, we can represent this as the antiderivative of each piece. The left-hand side is going to stay the same for a while, but the right-hand side, some interesting things are going to happen. I want to draw your attention to this term right here. Notice that that was the derivative of u times v dx. So if you take the derivative of something, and then you take the antiderivative of that thing, you get back what you started with. So if you take the derivative of u times v, and then you take the antiderivative of that, you get back u times v. So here, the integral, the indefinite integral, and the derivative cancel each other out, leaving us with just this u times v. Then the last term stays the same. Now, this last term, we have u prime times v dx. We can write u prime with Leibniz notation instead of Newtonian notation, which is du dx. This is important. So now that we've written this as du dx times v dx, we can see that the dx's are going to cancel. And that leaves us with a v and a du. So since we usually write our d term at the end, this becomes the integral of v times du. Now, if you go back to the left-hand side that we've been mostly ignoring, we can do the same thing with v prime. If we use Leibniz notation, it becomes dv dx. So the dx's cancel, and we get u dv. So u dv equals u times v minus the integral of v du. This is the formula that we use for integration by parts. Now, it doesn't work exactly the same as how we've been doing some of the other things. So it's important to understand how we use this formula. The original function that we're going to be studying is going to be your u dv. So the integral we're looking for is your u dv. Only it's not going to be u and dv, it's going to be functions of x. And what we have to do is we have to assign each of those functions to either u or dv. Once we do that, we'll be able to find v and du, and we will use that to plug into the right-hand side of the formula. So let's walk through an example and see how this formula applies. Example 1. Find the indefinite integral of x e to the x dx. So first we want to notice that we cannot do substitution here. One of the things we're going to need to do is we're going to be able to look at problems and determine if we need to use substitution or integration by parts. So here, there's no substitution we could make to make substitution work. Because if you let u equal your power of e, the derivative is 1. But we have an extra x out front. So substitution will not work. So that means we have two functions multiplied together that can't be solved with substitution. So that means that there's a good candidate here for integration by parts. So what we have to do is we have to match up our function with the first part of the formula, u dv. So that means we need to look at the two functions that have been multiplied together and determine which one will be our u and which one will be our dv. So we always pick our u first. So we have two functions, x and e to the x. When we pick our u, we want to pick something that when you take the derivative becomes simpler mathematically. So think about x. If you take the derivative of x, you get 1. A constant is simpler than a function, so that's a good candidate. And if we look at e to the x, the derivative of e to the x is e to the x. That's not any simpler. It's exactly the same. So here, we're going to pick our u to be x. Now, once you've picked your u, everything else becomes your dv. So dv here is e to the x dx. Whatever function comes over here to dv gets the dx with it. So now that we've picked our u and our dv, we need to do some side work to find the other pieces of the formula we need. So to go from u to du, that means we need to do an intermediate step. We need to take the derivative of u with respect to x. The derivative of u is 1, so du is 1 dx. So we multiply the dx up. Over on the right-hand side, if we want to go from dv to v, that means we're integrating both sides. On the left, we're finding the antiderivative of 1 dv. Since we have an invisible 1 here, that's a constant, and it'll pick up the variable of integration, which here is v on the left. On the right-hand side, we want to find the antiderivative of e to the x. The antiderivative of e to the x is e to the x. We don't need to worry about our plus c until the very end of this problem. We could carry it around the whole time, but what we'll find out is ultimately in the end, we just end up with a plus c on our final answer. So there's no need to carry it out until we have a solution. So what I want you to notice is that when we do integration by parts, we take both a derivative and an antiderivative. So you have to be really careful about which direction you're going to get the pieces you need. So what's key to doing this is remembering that the original function that we're looking for is u times dv. So once we pick our u and our dv, the u, you take the derivative, the dv, you take the antiderivative. Now we need to plug this into our formula to get our answer. Our formula says u times v, so x times e to the x minus the integral of v times du. So e to the x times 1 dx, anything times 1 is itself. So you may be thinking that it's a little bit strange that we have an integral in our answer, because the whole point of this was to try to get rid of the integral symbol by finding the antiderivative. But the goal here is that the antiderivative that we have to find in our formula is simpler than the one we started with. We should be able to go to our formula list and figure out the antiderivative, or maybe we already have it memorized. So our last step is to find the antiderivative that's in the formula. So the first term stays the same, x e to the x, and then the antiderivative of e to the x is e to the x. Now that I've done that step, my indefinite integral symbol is gone and my dx is gone, and I get my final answer. So here, my antiderivative is x e to the x minus e to the x plus c. This process is a little strange to get used to at first, but once you've done a few, it becomes very methodical, and not too hard to do as long as you're really confident in both your basic derivatives and your basic antiderivatives, because that's what this problem breaks down into. Once we know those, we're just applying the formula. So let's try another one. Example 2. We have x to the 6th times the natural log of x. Giving this a quick look, I don't see anything good that I would use for substitution. I don't have parentheses to a power, and my natural log doesn't have anything complicated on the inside. So this is a good candidate for integration by parts. I have to determine what my u is going to be. Again, I want to pick my u to be something that's simpler when you take the derivative. So x to the 6th has a derivative of 6x to the 5th. That's simpler because the power is 1 degree lower. However, the derivative of the natural log of x is 1 over x, and that is going to be simpler than the natural log of x. So both of these functions get a little bit simpler when you take the derivative. So we need to consider if we can take the antiderivative of both of these functions. The antiderivative of x to the 6th we can do with a power rule. We can add 1 to the power and divide by the new power. The antiderivative of the natural log of x is not something that's on our basics chart. We don't actually know how to do that yet. So we're going to pick our u to be the natural log of x. And in general, when you're doing integration by parts, if there's a natural log present in your problem, that's almost always your u. So that means that my dv is everything else. So that's x to the 6th dx. So now I want to take the derivative of the natural log, which is 1 over x dx, and I want to take the antiderivative of x to the 6th. So that becomes x to the 7th divided by 7. So I add 1 to the power, divide by the new power. So now my formula is u times v, so the natural log of x times x to the 7th over 7 minus the integral of v times du, x to the 7th over 7 times 1 over x dx. So before I take the antiderivative, I want to simplify that integral real quick to make everything a little bit easier. First, I'm going to pull the 1/7 out front. I like my constants in front. That's a matter of preference. Here, I have x to the 7th over x. So if I have 7 x's in the numerator and 1 in the denominator, the 1 in the denominator can cancel one of the x's in the numerator. So x to the 7th over x will simplify into x to the 6th. So this becomes x to the 6th dx. So now the first term stays the same, the natural log of x times x to the 7th over 7 minus 1/7, which is my constant multiple, and I want to take the antiderivative of x to the 6th. So that becomes x to the 7th over 7. So I could combine the 7's in my second term to make 49, but that's the only simplification I would do. So again, when I do integration by parts, the goal is that the integral in the formula will be something I can actually take the antiderivative of. But it's always a good idea to simplify before you do the antiderivative if possible. So combining any constants, or as in this case, simplifying x terms. Let's look at another example. Example 3. 8x cosine of 2x dx. Now, you might look at this problem and think that we might be able to do substitution. Here, if you were considering substitution, your u would be the function inside cosine, which is 2x. But that means your du would be 2, and that's problematic because we have an 8x on the outside, not just an 8. So that means that we're not going to be able to use substitution here. Instead, we're going to use integration by parts. So my two functions are 8x and cosine of 2x. Again, we want to pick our u to be something that becomes simpler when you take the derivative. The derivative of 8x is going to be 8. The derivative of cosine is going to be negative sine, right, with a chain rule. So sine is definitely not easier than cosine. They're equivalent. So that means the term that gets easier when you take the derivative is 8x. So that's going to be my u. So my u here is 8x, which means my dv is everything else, which is cosine 2x dx. Now I need to take the derivative of 8x, which gives me 8 dx, and the antiderivative of cosine. So the antiderivative of cosine, we have to remember that if there's a number that's in the argument, we have to divide by that number in the end, right? So the antiderivative of cosine is sine, so we have sine of 2x, but we have to divide by 2 because we're taking the antiderivative, so we divide by that constant. Now, I want to apply my formula. So I'm going to do u times v. So I have 8x times sine of 2x divided by 2 minus the integral of v times du. So sine of 2x over 2 times 8 dx. I'm going to do a simplification step here. In the first term, I have an 8 and a divided by 2. So I'm going to write that as 4x sine 2x minus, now here again I have an 8 over 2, which is going to be 4. So I'm going to pull that out front. So I have 4 sine of 2x dx. So now I want to take the antiderivative here of this integral. So the first term stays the same, 4x sine of 2x minus 4 times. Now the antiderivative of sine is going to be negative cosine. So here we have negative cosine of 2x, and again we're dividing by 2, because every time you take an antiderivative of one of the trigonometric terms, because there's that 2 in the argument, we have to divide by 2 again. So simplifying this last term a bit, the first term will stay the same, 4x sine of 2x, but then here I have a negative and a minus, so that will become plus, and then I have a 4 divided by 2, so 2 cosine 2x. So our final answer looks like this after going through the careful process of integration by parts. Let's try another one. Example 4. Here we have the indefinite integral of the natural log of x dx. This may be a little deceiving because it doesn't look particularly like any of the other problems we've been doing. All of the other problems that we've been doing have either been on the basics antiderivative chart, which this is not, or had two functions multiplied together, which this does not either. However, we can still do this problem, but we have to use integration by parts. Now, think about the function natural log of x. If we made that our dv, that would be problematic because we need to find the antiderivative of the natural log of x. And that's exactly what this problem is. So if we knew the answer to that, we wouldn't have to do integration by parts. However, if we make our u the natural log of x, let's see if anything interesting happens. So if u is the natural log of x, your dv is everything else. Well, everything else here is just dx. The derivative, du, of the natural log of x is 1 over x dx. And the antiderivative of 1 dx becomes x because there's an invisible 1 there. So when you take the antiderivative, it picks up the variable of integration. So when we put this together, we're going to do u times v, so the natural log of x times x, minus the integral of v times du, so x times 1 over x dx. So let's simplify our integral before we integrate here. If you have x times 1 over x, the x's are going to cancel, and you're left with 1 dx. So the first term stays the same, natural log of x times x, minus the antiderivative of 1 dx is again just going to be x, because the 1 is a constant and it picks up the variable of integration, which here is x. So I end up with the natural log of x times x minus x plus c. So this one is really a little bit, not ordinary, because the natural log of x looks like something very simple that should be on our basics chart, but it's not, because the only way we can find the antiderivative is by doing integration by parts, and you end up with something somewhat unexpected. With one single function, like the natural log of x, you end up with something pretty complicated, the natural log of x times x minus x. So it's a really interesting problem because it's unexpected. Let's look at another example. Example 5. X squared e to the 4x. So again, we need to start by looking at our two functions and determining which one's going to be our u and which one's going to be our dv. If we consider the two functions, we know that e does not get simpler when you take the derivative. In fact, it stays pretty much the same. So we know that's probably not going to be e, which means that our u is going to be the x squared term. So dv is everything else, which is e to the 4x dx. So du, the derivative of u, will be 2x dx, and v, the antiderivative of e to the 4x, is e to the 4x divided by 4. So remember the extra special formula we had where if you have a constant up in the power, you have to remember to divide by that constant. So now we have all our pieces and we're going to put them back together using our formula. So we're going to do u times v. So x squared times e to the 4x over 4 minus the integral of v e to the 4x over 4 times du. So times 2x dx. Let's simplify. So we have x squared e to the 4x over 4 minus, let's pull out our constant, which is 2 over 4, which is the same thing as 1/2, integral of e to the 4x times x dx. So at this point, you may have some concerns. I have some concerns. Normally, when we get to this step, the antiderivative we have to find is one that we can do using the basics chart. But here, I have an integral that has two functions multiplied together, which means I can't just use the chart to find the antiderivative. So does that mean we did something wrong? Well, the answer is maybe. So if you're doing integration by parts, and you get to the part where you're looking at the integral that's part of the formula, and it's not something you can do from the antiderivative formula chart, you need to consider whether or not the function that you are now looking at in the formula is simpler than the one you started with. If the answer is no, if it's not simpler than the one you started with, then maybe you shouldn't have done integration by parts. Perhaps it was a substitution problem and you didn't realize, or maybe you were supposed to simplify the original function. However, if it is simpler, then that means you might need to do integration by parts twice. So notice here that my new integral is e to the 4x times x. So e to the 4x stayed the same, but before I had an x squared, and now I have an x to the 1 power. So that is simpler than the integral I started with. So I need to keep going. So what's going to happen? My first term stays the same. E to the 4x over 4 times x squared minus 1/2. But now I need to do another integration by parts. But now my two functions are e to the 4x and x. So again, my u is going to be x because that's going to get simpler when I take the derivative. The derivative of x is going to be 1 dx. So that's promising. Now we're down to a constant. My dv was everything else. So e to the 4x dx. So my v is e to the 4x over 4, right? Should seem familiar. So now I need to take my result and I need to plug it into the parentheses because that negative half term, it has to multiply my whole result. So I'm going to do u times v. So x e to the 4x over 4 minus the integral of v du. So e to the 4x over 4 times dx. So I need to do some work here. I need to do this integral that was part of my formula, and I need to distribute the 1/2 power. So let's do the integral first, and we'll do the distribution second. So here, first term stays the same. Nothing's been changing there since the beginning. Minus 1/2 times x e to the 4x over 4 minus. Now, when you take the antiderivative here, normally I would pull the 1/4 out front before I did the antiderivative, but I'm running out of space, so I'm not going to do that. So instead, I'm just going to reason through this. If we had the 1/4 out front, it would be the constant multiple that multiplied the antiderivative of e to the 4x. We know from both of our setups here that the antiderivative of e to the 4x is e to the 4x over 4. Which means that when I do this integral here, another 4 is going to come out when I find the antiderivative. So that means I'm going to have minus e to the 4x over 16. So again, another 4 came out when I did the antiderivative. So now, last but not least, I need to distribute the negative half that's in front here. So my first term stays the same, x squared e to the 4x over 4. Now, I'm going to have minus, when I multiply the half times the first term, I get x e to the 4x over 8, because I have 2 times 4. And then I'm going to have plus, because the minus in front of the half is going to cancel the minus in front of the last term. And that'll be e to the 4x over 32, because I have 2 times 16. So my final answer looks like this. And I can tell you that I knew, just looking at the original problem, that I was going to have to do integration by parts twice. And the way I knew that was because I had an x squared term. If I had a linear term like x or 5x, then integration by parts will only happen once. But if you have an x squared term times either an e term or a trig function, you may have to do it twice. But remember, the way we determine that is when we've plugged everything into our formula the first time through and we look at the integral in the formula. That's what helps us decide if we have to do it again. But we were able to reason through and keep going and come up with our final answer. Let's look at one more problem. Example 6. So in an earlier section, we looked at surge functions. And surge functions were going to tell us the amount of drug found in the bloodstream after time t. However, surge functions also represent the rate at which the drug is being absorbed into the bloodstream. We talked about the bioavailability of the drug in an earlier section, which had to do with absorption. So knowing that the surge function represents a rate, and knowing that the surge function is of the form at e to the negative bt, we want to find a function to represent the total amount of drug absorbed after time t. So what that means is we want to consider this as a rate, and we want to find the antiderivative. So here we want to find the antiderivative of at e to the negative bt dt. If we're able to find that antiderivative, that will be a function that represents the total amount of drug absorbed after time t. So notice here that we have two functions multiplied together that have the variable. We have at and e to the negative bt. There's not a very good case for substitution here, so we're going to try it with integration by parts and see what happens. So again, my first function is at, and my second function is e to the negative bt. When I pick my u, I want to pick something that gets simpler when I take the derivative. So at is something that's going to become simpler because the derivative of at is just the constant a. So here U is AT, so my dV is everything else, e to the negative bt dt. So my du, the derivative of AT, is A, and my V is the antiderivative of e to the negative bt, which is e to the negative bt divided by negative b. So think about the last problem we did when we had a constant up in the power. When we found the antiderivative, we had to divide by that constant. The same thing's happening here because b represents some constant. So now that we have all our pieces, oh, we forgot our dt, sorry, this is a dt. We want to plug them into our formula. So we're going to do u times v. So we have AT times e to the negative bt divided by negative b minus the integral of v times du. So e to the negative bt divided by negative b times a dt. There's a lot of constants here, okay? So I'm going to try to combine some things to simplify and make this a little bit easier to read. So from the first term, I'm going to pull the negative out front and write this as negative a over b te to the negative bt. So the reason I wrote it that way is because I wanted to combine the constants a and b to be together since they're just constants here. Now, from my integral over here, I have a minus, but then I have a negative b down here. So that negative will cancel the negative out front, and I'll get plus. Now again, I'm going to combine my constants and pull them out front. So AB integral e to the negative bt dt. So the first term, again, is going to stay the same here. So negative AB t e to the negative bt plus a over b. Now I want to find the antiderivative of e to the negative bt. So that's e to the negative bt over negative b. So again, when we take the antiderivative, another negative b comes out. Let's do one more step to simplify just a little bit to make sure that we have our final function in good form. So again, the first term stays the same. Negative a over b times te to the negative bt. Now the negative from down here, I can pull out front and make that minus. Now I'm going to have a over b squared, because I have two b's in the bottom, times e to the negative bt. So this is going to be my function that represents absorption, the total amount of the drug absorbed. And I did that by finding the antiderivative of the surge function, which is the rate of absorption. So again, I could do that using integration by parts because I have two functions multiplied together, and when I do them out and I use the pieces, I'm able to put them together in such a way that in the formula, I'm able to take the antiderivative of e to the negative bt, which allowed me to finish the problem.